Okay, great. Hi, guys. Welcome to the second session of our SUMAC workshop. This session is called Browsing, Visualization, and Interaction in Multimedia Heritage Contents. And to begin with this session, we will start with a keynote from Livio de Luca. I'm going to give a short, brief introduction to who Livio is, who our second keynote talk is about. So Livio is architect, a doctor of arts at Métiers at Paris Tech, HDR in computer science. He is the research director of CNRS and director of UMR CNRS, MCC MAP, which is Models and Simulations for Architecture and Heritage. His research activities mainly focus on the survey, geometric modeling, and semantic enrichment of digital representations of heritage objects, as well as on the design and development of multidimensional information systems. Livio has been the associate editor of 2 international journals, which are directly related to the overall theme of our workshop. One is by Elsevier, called Journal of Cultural Heritage, and ACM Journal on Computing and Cultural Heritage. Since 2016, he has been appointed member of the National Committee for Scientific Research. His work was awarded in 2007 by Pierre Bezier Prize from Arts at Métiers Foundation, and in 2016 by the Research and Technical Medal from the Academy of Architecture, and in 2019 by the CNRS Innovation Medal. He is currently the coordinator of the Digital Data Working Group of CNRS Scientific Project and the Ministry of Culture for the restoration of Notre-Dame de Paris. Which brings us to the topic of his talk today, which is towards the semantic-aware 3D digitization of architectural heritage, specifically for the Notre-Dame de Paris digital twin project. I heartily want to welcome and invite Livio to please present his talk. We are very excited about it. Thanks a lot again for being here with us, and the stage is yours.
Okay. Good morning, all, and thank you very much for this invitation. I would like to thank all the organizers, Valerie, Margarita, Ronak, Xunchen, and Liming for this invitation. My presentation concerns a project implemented by the CNRS and the Ministry of Culture around the restoration of the Notre-Dame de Paris Cathedral. As you can imagine, I cannot present scientific results for the moment, a little more than 1 year after the fire of Notre Dame, and especially concerning your field, which is not exactly mine. But I think my presentation can give you a good idea of the problems associated with a real restoration work site. My presentation may also allow you to identify potential applications of the methods you are working on, especially with regards to the machine learning, because as you well discovered in my presentation today, we are mainly oriented towards the collection of digital data semantically enriched by humans. So first, a few words about the scientific action. After the fire on April 15, 2019, through a spontaneous initiative, hundreds of researchers get done. For this, the CNRS and the Ministry of Culture have set up a major scientific action, bringing together members of more than 50 research laboratories in France by forming 8 working groups. First of all, working groups on materials such as stone, wood, metal, stained glass, then on structural and acoustic behaviors, as well as on the more social dimensions related to the heritage emotions. These working groups involve researchers from multiple disciplinary sectors such as physics, chemistry, geology, archaeology, architecture, history, engineering, anthropology, and sociology. And the last working group, which is cross-cutting to the other 7, and which I have the honor to coordinate, focuses on digital data. The Digital Data Working Group is made of 9 research laboratories, 2 consortia of the CNRS very large facility, Humanium, and today brings together around 30 researchers and engineers from the CNRS, the Ministry of Culture, as well as several French universities. And this working group also draws on a framework of international cooperation through targeted invitations sent to some researchers recognized for particular skills. The working group includes engineers, architects, historians, and computer scientists by bringing together research STEM and skills in metrology, geometric analysis, and reconstruction, but also design and development of information system, as well as in virtual environments for the construction of historical hypotheses. As you are all specialists in matter related to the calculated data, it's very easy to understand that this project, which was born spontaneously around an emblematic issue and an emblematic heritage object, quickly became for the French community the ideal context to bring together the forces, initiatives, and the results already achieved, to try to build a collective challenge around this historic project. And I can assure that as a scientist, use it to define medium and long-term challenges based on theoretical assumptions. It's really difficult to manage a scientific action to serve a work site that must act in the emergency and plan actions in a very, very short term. Nevertheless, we all agreed that it was really necessary to leave aside the aspects related to the conceptualization and try to respond pragmatically to certain needs of the restoration worksite. So in order to register our activities directly within the restoration service, we have therefore established a strong relationship with the base of the restoration worksite by organizing several meetings with the chief architects of historic monuments, the regional archaeological service, as well as the historical monument research laboratory. These are the 3 main actors on the restoration worksite who are in the cathedral from the evening of the fire and who monitor activities related to the study of the monument stability, the archaeological excavations, as well as to the daily inventory and analysis of the remains. At the end of the multiple meetings with these actors, we were able to retain the essential needs, which concerns the scientific knowledge on materials, behaviors, and shapes, before, during, and after the fire. And this corresponds to specific challenges for the working group on digital data, which concern the data management for documentary research, the data management for diagnosis, some tools for the analysis of structures, spaces, shapes, and materials, and of course, virtual models for simulation and decision making. So to give you an idea of the state of the cathedral was after the fire, here are some pictures. The roofs burned by dropping the spire and causing part of the vaults to collapse at several points. And from these challenges, we were able to bring together skills around major categories of problems. First, the comparative analysis of temporal states, essentially before and after the fire, in order to evaluate the alteration undergone by the vaults and other structures. Then the simulation of the mechanical behavior of structure, but also the acoustic behavior of spaces. The data and information management for diagnosis and for monitoring restoration activities, taking into account detailed description of the building's sanitary condition and the damage suffered by the fire, and of course, a virtual reconstruction of the missing elements, in particular, the frameworks, the vaults, today represented by masses of partially destroyed elements of wood, stone, metal, fallen on the upper surface of the vaults or directly on the ground. Anyway, if we were quickly able to identify what the digital science and digital technology could do for the restoration of Notre Dame, we also understood what the restoration of Notre Dame could do for all the heritage science, especially concerning the digital sphere, to force us to collectively move towards the production of a collaborative working environment able of making the semantically enriched data the core dimension for the multidisciplinary scientific research of cultural heritage. So within this working group, we have the ambition to design and to develop a digital ecosystem, including a platform for the collection of data and the collaborative production of knowledge, an informative system to memorize in space and over time activities produced by multiple actors and within a multidisciplinary framework. And we believe that this ecosystem should become a real interface between the scientific work side and the restoration work side. In view of the large number of scientists included in this project, as well as the heterogeneity of the approaches, this requires the definition of a complex implementation plan and to be carried out very quickly, unfortunately. And this plan includes definition of methodological approaches for producing semantically enriched data, the confrontation with some operating modes of the different working groups with different profile, and a continuous reflection on the data life cycle, but also the development of ad hoc digital tools for gathering, processing, categorize, and correlate multidimensional data. So let me start from this last point, and let me focus on the state of the art on semantic enriched 3D representation in this regard, because the Notre-Dame Digital Twin project is above all a question of architectural representation, but at the same time a question of knowledge representation. So when we talk about knowledge and cultural heritage, we must have to understand that cultural heritage is a complex ecosystem because it includes several activities such as the access, the study, the conservation, the interpretation, the management of data. These activities are made by several actors such as scientists, practitioners, administrators, and all these actors look at the same object by using different approaches coming from the cultural or scientific background. Yes, because cultural heritage is a cross-cutting knowledge area, bringing together humanities and social sciences, as well as the experimental fundamental sciences. This context generates strong heterogeneity. We have to manage the relationships between object, materials, observation, and acquisition devices, several methods of analysis, data formats, information, conventions of description, different terminology and operation protocols, and so on. And these topics are today addressed by a cross-disciplinary scientific community that merge contributions coming from the engineering and the computer science sectors about the methods and tools for the acquisition, the observation, the multidimensional analysis on one hand, and on the other hand, by the cultural heritage experts who are renewing their daily practice for surveying, for documentation, study, and communication. And these issues crosses two main topics by integrating methodological and technological aspects. The reality-based 3D reconstruction on one side and information systems on the other side. You know very well that reality-based 3D is considered as the research area based on the use of active, range, or passive image sensors for creating digital replicas of real objects and scenes. And thanks to the advances in photogrammetry and computer vision, the last few years have been characterized by an impressive growth of image-based modeling approaches, able to automatically reconstruct dense 3D point clouds and meshes from a set of non-oriented photographs. From a methodological point of view, some of our contributions in this area focused on the introduction of customized methods for specialized processing workflows, as well as some photographer-friendly acquisition protocols to be used in the real cult-layer digital documentation scenarios. So beyond the geometric and the visual representation of shapes, a large amount of data is usually collected, organized, and analyzed for the study of cult-layer artifact. And this topic is certainly the main focus of your community, and several works are focused on the management of linkable digital contents by introducing formal structures describing implicit or explicit conceptual elements and their interrelationships, or some methods focused on enriching documents with geotags. Other works focused on solutions for adding semantic tags to ortho images on 2D images, or pre-structured 3D representation of heritage objects. And finally, a trending topic today concerns the linking of the 3D digitization of existing buildings with the building information modeling, so the BIM paradigm. Within this area, our previous contribution consisted in introducing models and methods for structuring of morphological descriptions within the interlinking of multiple 3D representations and resources. And by these works, we highlighted the potential for the semantically enriched 3D reconstruction in two areas. First of all, for structuring iconographic documentation around 3D models, then for managing data on materials within the conservation and restoration applications. So reality-based 3D reconstruction and the 3D information systems are generally considered as distinct topics. A few projects consider them as complementary parts of an unique framework. On one side, works on the management of the documentation activities are mainly knowledge-centered, with no explicit or direct exploitation of geometric and visual properties belonging to the 3D representations. On the other side, the approaches based on the 3D annotation of reality-based models are mainly object-centered, with no reference to the complex relationships that shape the documentation and the interpretation process. So to merge geometry, visual appearance, and semantics within an integrated documentation approach is an important topic today. And this issue includes three major gaps. First, a semantic gap. Because if the development of digitization machines and the implementation of crowdsourcing strategies for the massive gathering of digital replicas of calculated objects is to become a realistic perspective today, the growing mass of uninterpreted point clouds and 3D models is underlining an essential need in this area. So the need for innovative methodologies for assisting data processing, sorting, and analysis towards an effective knowledge enhancement scenario. Second, a communication gap, because the use of digital tools is today included in more and more consolidated observation and analysis protocols according to several aspects of a calculated artifact. And this underlines the need for effective solutions for collecting, storing, sharing data, and extracted information. while it's still difficult to bring together physically or digitally the multiple actors of this continuous documentation process carried out on objects. Third, an interoperability gap. As you know very well, structuring heterogeneous data belonging to the same heritage artifact still remains a critical issue today. If one hand, file-centered approaches use unstable anchors, such as metadata, terminology, conceptual reference models, for establishing semantic links between digital resources belonging to the same physical object. On the other hand, the 3D-centered approaches presented above, also including our previous work, are limited to the adoption of some static representation, sometimes with a pre-established segmentation that strongly constrains the data structuring strategy. And this underlines the essential need for a flexible solution allowing us to manage several acquisitions, levels of detail, geometry, segmentations, annotation layers, and data properties according to the very heterogeneous observation and analysis scenarios. These are the starting points of the Aioli project. Aioli is a reality-based 3D annotation platform for the collaborative documentation. This platform is today at the center of our scientific action on Notre-Dame de Paris. Our approach considers the real object, the physical one, as the stable denominator from a conceptual and from a technical point of view for structuring data and annotation coming from a continuous process of observation and analysis carried by multiple actors. By considering reality-based 3D and semantic description in a strongly integrated way, we build an informative continuum based on three essential features. First, a continuous 3D mapping and annotation process. So we establish like a bridge between the real object, its perception, and its digital representation, able to memorize specialized annotations made by different actors. Then a morphology-based data structuring approach based on a multi-layer description model for the simultaneous structuring of geometric and user descriptors. Then a flexible and scalable technology allowing the gathering, the processing, the sharing of semantically enriched 3D data within online and on-site documentation scenarios. Concerning the continuous 3D mapping and annotation process, we developed an incremental image-based 3D specialization process by basing on Micmac, a photogrammetric software developed at the EGN in France. This incremental process allows us to progressively merge into unique 3D scenes, sets of images acquired by several actors. This allows us to progressively build dense 3D point clouds that are first indexed, then reprojected into the specialized 2D images by exploiting the computed cameras calibration and orientation parameters. Thus, for each image, an array is created for storing indexes of the 3D points corresponding to the projected pixels. So during this process, some geometric descriptors such as normals, curvature, ambient occlusions, etc., are also computed on the 3D point clouds and coded in formats, then reprojected on the original images. By this way, simple 2D images can be used by the platform users for annotation purposes. We recover contours directly drawn by the users on the images in order to isolate specific image regions, but at the same time, we can also exploit the computed geometric properties reprojected onto images in order to extend user selections to similar regions. In both cases, after the selection of an image region, a list of 3D indexes is extracted from the used image, then mapped with the main 3D point cloud, and finally compared with the images belonging to, for the indexes belonging to all the images on which the selected region is visible. The selected spatial region is then accurately located in the 3D space as a segmented point-based representation, and as well on all the 2D images as a vector-based representation. This is to be considered as a continuous process because, as explained, new images can be oriented towards an existing dataset. So thanks to this 3D to 2D projection mechanism, existing registered annotations can be automatically reprojected onto new images. Moreover, new annotation can be drawn on the recently added images and propagated onto the entire image set and so on. From a software implementation points of view, we ensure this 2D, 3D annotation process by a set of backend Dockers in charge of all the processing steps, from the image 3D specialization to the extraction of geometric and visual descriptors related to the isolated annotation. And these processes are called by a web service with a responsive interface, so usable also in on-site scenarios. Concerning our data structuring approach, we consider 3 layers. First, the semantic layers, which integrates and organizes a set of freely structured user descriptors to define specific aspects of an heritage artifact according to an application context. A morphological layer, which brings together computed geometric and visual descriptors resulting from the extracted 3D spatial regions to enrich user descriptors by complementary aspects needed for the geometrical analysis of the regions. Then a spatiotemporal layer, which explicits the relationships between the acquisition of 2D images and the annotation of the 3D forms over time. It constitutes the framework for the analysis of the spatial and the temporal distribution of user descriptors and the computed descriptors within the use of the platform. So within IOLE, data structured around the same annotation are linked to an actor belonging to an application driven on a specific heritage asset and can be always used for data linkage purposes. In fact, the 3D regions partially share the same spatial region on the real object. For example, an annotated region concerning a figure on detail could overlap another annotation region concerning a degradation phenomena and so on. The spatial overlapping between annotated regions belonging to different annotation layers is then used as a primer for the semantic linkage process. This action is embedded into the 2D and 3D propagation process and allow identify overlapped annotation by referring to the general indexing of the backend 3D point cloud. The correlation process is then used to create relationships between the annotation as well as between the related user descriptors linked to these annotations. So we believe that this mechanism is very flexible, and allow the generation of hundreds of relationships between concepts used for the annotation of the same object in a very spontaneous way. In fact, the recursive linkage of human and computer descriptors belonging to the overlapped annotations generates a rich environment for training, and this could be very relevant for your community, but also for the analysis of and the interpretation of some co-occurrences of factors in heritage science. For example, a given material is generally used for a given building technique, or a category of figures is mainly represented on a given type of ornament, or a degradation phenomenon is mainly observed on element with a given orientation, and so on. So we intend to explore the potential of this correlation framework in further works by assessing its applicability at several scales. For example, by correlating annotation layers belonging to an unique objects, or to a collection of objects, as well as by analyzing the variability of attributes belonging to the same concept. For example, a vocabulary term. So let's go back to the Notre-Dame project, because as you can easily understand, this project is an excellent framework for experimenting the potential of the reality-based 3D annotation with IOLI. I will now show you some images of the work in progress on two subjects concerning the restoration site. First, the work on the forest, the framework of the roofs. The remains of the burned roofs were, and still are in part, on the upper surface of the cathedral vaults. So there was a long and difficult operation to collect and inventory these elements. It is a real archaeological excavation that we are currently monitoring through acquisitions by 3D laser scanners, as well as by a specific device that we designed and developed for the project, which allow to acquire thousands of photographs in an automatic way along the rails installed above the vaults. And this make it possible to record very quickly in 2D and in 3D all steps of the removal operations. And here you can see the level of resolutions required to record this precious information for the identification of each element, as well as for its spatial and temporal location before the fire, after the fire, and during the removal operations. And then its temporary storage outside the cathedral. For the spatial temporal location of each element, we are in the process of setting up several image-based 3D scenes within the IOLI platform. As you can see on the images, this make it possible to identify the elements on the images by the annotation, a simple 2D annotation, then to locate them within the 3D point cloud from the same images, and to enrich each annotation with descriptors and comments and the complementary sources made by the researchers involved in the project. So the analysis of the remains is done in parallel with another action which concerns the geometric reconstruction of the previous state of the roofs from the existing surveys, so traditional and digital ones, surveys carried out before the fire and today at the disposal of the scientific action. As you can imagine, this is a complex task because it requires the continuous confrontation of drawings, hundreds of photographs, 2D and 3D coordinates, but above all, the confrontation with the state of the remains of the roofs after fire. And This implies taking into account also, from a conceptual point of view, important issues on the semantic structuring of the 3D representation, the 3D final representation, because for each entity of the previous state, for example, a beam of a form, can exist today several fragments within the remains to be connected. Another subject on which we are working today concerns the valves, in particular the comparison of their state before and after fire. This is a fine geometric analysis that we are able to carry out by aligning 3D laser scans carried out before and after the fire. And this comparison allows studying the deformations undergone by the valves due to the fire, and will be used later to the study of aspects related to the structural behavior. We were also able to take into account the visual appearance dimension of the surfaces, since we had hundreds of photographs on the valves before fire, and this allowed us to map surface deterioration phenomena useful for the diagnosis, and which could be annotated within the Aioli platform, as you can see on the images. So on the same scenes in Aioli, we will soon add some spatial location of the samples taken from the vault, from the characterization of materials and the degradation phenomena. Still, on the vaults, there are more perspective issues emerging today, in particular with regard to the space-time tracking of blocks that have fallen into the nave, and this by the means of automatic analysis and classification methods used on thousands of images acquired during the first days of intervention after the fire. This issue, very complex as you can imagine, could bring very important help to the restoration site, particularly with regard to the reuse of some original elements in the restoration project. We just started a collaboration with Valérie Gouet and Władysław on this subject. On one hand, we intend to evaluate the potential of image monomodal or multimodal indexing methods by learning in scenarios of analysis of complex transformations at the scale of the monumental architecture. And on the other hand, we will explore knowledge graph embeddings approaches to introduce scalable similarity measures in heterogeneous semantic graphs. And these graphs should combine the properties and the relationships at the conceptual level of the annotations accumulated on the spatially oriented photographs with Aioli. So in my presentation, I've focused on the specific issue of the semantic enrichment of reality-based 3D representation, and I have shown the first applications of the Aioli platform to Notre-Dame. But I want to underline that Aioli is just a module of the digital ecosystem we are building for this project. What I'm showing now on the screen is a very first diagram of the platform we started to prototype since last February. This is just a first draft, and I'm sorry because the schema is in French, but the platform includes 3 interconnected sectors. On the left, the data collection. On the top right, the data enrichment modules, and on the bottom right, the correlation engine. First, data collection. So regarding the collection of data, thanks to the legal framework put in place by the Ministry of Culture at the CNRS, we were able to recover thousands of files from cultural institutions, laboratories, companies in the conservation and restoration sectors. And these include documentary sources, technical reports, photographs, 3D scans, and existing database, and several studies related to the older restorations of the cathedrals. And today we have already gathered 10 terabytes of files, to which are gradually adding all the data that the scientific site is producing and will produce in the coming years. The collection and the storing of this resource is based on a toolbox developed by the Humanum very large facility of CNRS, bringing together solution for managing user accounts, secure storage, sharing, and collaboration tools. But also some solutions for the long-term archiving, in particular on the basis of the standardization work led by two consortia involved in the project. Regarding the data enrichment, we have already assembled 3 modules specialized on the documentary categorization, the semantic categorization, and the 3D specialization and annotation. These are all tools based on web technologies coming from the research laboratories involved in the project. First of all, ArcuGrid, which allow to document and catalog digital resources by means of common metadata sets and composed on the basis of the requirements of the projects and already aligned to some standards of the domain. The metadata concern provenance, condition of use, technical specification, as well spatial and temporal location in relation to the cathedral, and also some labeling and description based on thesauri developed by all the project working groups. The management of the controlled vocabularies is based on OpenTheso, and this tool allows the collaborative creation of a thesaurus, today under definition, including terms of description related to the architecture, the building and restoration techniques, materials, degradation phenomena, as well as some methods for the scientific analysis, the instruments, and all the actors involved in the scientific and restoration action. And the third module is IOLI that I have already largely presented today. I just add that within the Notre-Dame project, we are adding specific features to IOLI in order to use controlled vocabulary, particular with the link by the link with OpenTheso. And as you can imagine, from a scientific point of view, the most challenging aspect of this project concern the data correlation scenarios. I can't present any result yet, but for the moment, I can anticipate that we plan to take into account 4 complementary aspects. First, the space, by the 3D specialization of iconographic sources, but also by labeling and annotation mechanism. So the form, by basing on the segmentation methods developed with respect to several points of view and several levels of reading of the same shapes. Third, the time, in particular by analyzing the transformations resulting from the comparison of several temporal states that we are registering today. And at the end, the knowledge through the analysis of the thematic overlaps resulting from multiple disciplinary perspectives on the spaces, on the forms, and on the transformations. So from this, we intend to analyze the spatial and also the semantic proximity of clusters of 3D annotations coming from the IOLI platform. And finally, concerning the visual exploration of the data gathered and enriched within the platform, we just started to develop a specific web viewer, and of which you can see a first video on the screen. It is a 3D visualization framework based on Three.js and Po3.js, which allow users to navigate within the multiple resources related to the cathedral while bringing together the link to the original data stored in the platform. This is possible by the connection between this viewer and the ArcoGrid, which allow, for example, to recover metadata relating to the 3D point cloud, or even related to a specific specialized photograph. This allow users to recover the link to vocabulary terms in OpenTeso, and it also allow to do measurement or visualize other types of geometric representation or to visualize sets of 3D annotations coming from Aioli platform, as you can see now on the screen. We are currently adding some features for the collaborative annotation and the comment, and in the future we'll plan to start developing new features for exploring the corpus, in particular in relation to the correlation engine. So the idea is to introduce a set of visual interface to explore the corpus from a spatial, temporal, and semantic point of view, in particular by crossing notion of spatial proximity within the 3D representation with notions of semantic proximity within the knowledge representation.
Hi. Yeah, there was a patient video. Maybe he has frozen, right? Maybe.
Notre-Dame fire. So I presented just the first steps of the scientific action on digital data. So we probably need at least 4 more years of work for helping the restoration by collecting and by producing data. And given the masses of data to be processed, we are today looking to the introduction of semi-automatic and automatic solutions for spatio-temporal distribution of data, for the multimodal spreading of semantic attributes among data, and of course for the data correlation. And I believe that this project will produce an emblematic sampling of heritage science data, and we will probably need more years of work after the restoration of the cathedral to analyze this emblematic sample produced by a collective adventure. So I will stop here and thank you very much for your attention.
Thank you very much, Livio, for your beautiful presentation, showing us the complexities and the intricacies involved in the research action group, where we try to recreate the digital heritage using 3D methods. It was very interesting for me. I learned a lot of things. And now I open the chat for the questions. We already have one question. Should I just go ahead and read it out to you?
Yeah.
Okay. So the question is, how do you manage the different versions of a digital object due to the multiplicity of the sources? Do you plan to exploit this multiplicity to ensure the quality or the veracity of the stored information?
Oh, this is a very, very interesting question, and we worked some years ago on this problem of the versioning of the especially concerning the hypothetical reconstruction. At the moment, we didn't explore this problem within the definition of the digital ecosystem in the Notre-Dame project. But in previous works, we used a versioning mechanism allowing to manage parallel versions of the same representation and allowing to attach each comment or each attribute coming from experts to a given hypothesis. So this allow to introduce like a voting process that put to the 3D hypothetical representation, for example, some attributes coming from the qualitative interpretation of the objects.
Okay, thanks a lot for the answer. I have a question of my own. So in the beginning, when you described how to correlate the user-generated descriptors with the computer-generated descriptors, and finding how there is an overlap between them, and then finding a corresponding descriptors for that overlap, and then going back to the 2D images or the samples that you already have. This seems to be a very complex and computationally heavy task, given that you find an overlap. So let's assume that you find an overlap. However, it's still a very computationally heavy task. Can you comment on this? How do you handle this complexity?
Yeah, we have two levels of comparison and analysis of the overlapping mechanism. First, when we compute the 2D, 3D, and 3D, 2D spreading, we also compute some very basic geometric descriptions, such as like a bounded box of the annotation. So on this bounding box, we can easily compute an intersections with other bounding box in space. Then if the intersection is detected, so we can enter into a specific analysis of the number of indexes, 3D indexes common to two concepts. So we can do that in order to attribute specific overlap rate of each overlapped annotation. And this mechanism is under work today, but we never tested it on big scenes, including thousands of annotations. But the Notre-Dame project will force us to do it.
Okay, thank you very much. In response to the previous question, is this voting that you mentioned considered as a definitive or commit?
No.
Okay. Okay, thanks. Another comment is, thank you for the talk. It is really an immense project. I just wonder, do you have also the digital models of the cathedral before the fire with the same level of details?
Yes, we recovered several point clouds before the fire. The most important is the work from Andrew Talon, who's a professor of the Vassar College in New York. And this is probably the most complete 3D digitization of the cathedral before the fire. But unfortunately, the 3D laser scanning, the density of the point cloud is not really sufficient for the analysis and the recovering of geometric information on each block, especially concerning the blocks of the vaults we are studying today. And this is why we are looking on two solutions. First, the collection of thousands of photographs from a crowd sourcing initiative, even if this is not really relevant for us, because we really need for high detailed photographs of the previous states, and this is not typically what the tourist can acquire. And on the other side, we are looking to some super resolutions approaches for trying to interpolate values within the reflectance attributes into the 3D point clouds coming from the laser scanning, in order to highlight some details not very well visible today, such as the limits between a block and another block within the vault structure.
Okay, thanks a lot again for your response. I don't see any more comments. We do have 1 minute left, at least. So, guys, if you have more questions, please comment it here and I will read it out. Okay, there is an interesting question now. Is the system reserved for experts or can it be open for the general public?
Oh, this is a good question. From a purely technical point of view, it could be open to the general public. But as you know, this is an emblematic project, and there are a lot of problems related to diffusion of information about the restoration site. But anyway, we intend to open a specific version for the general public. And we are already thinking about a specific low resolution version of the web platform, allowing to project just very simple data coming from the scientific site today. In any case, we already established that 2 or 3 years after the production of each data coming from the scientific action, this data will be fully open and accessible to all the public, because we intend to provide scientific data coming from an open science approach.
Great. That's very good news, actually, for the research community. Thanks again.
And I hope that we can really share this. It depends on some political decisions concerning the use and the reuse of several sources, important sources that have been made available to the scientists today. But if we arrive to do this, we intend to open all the mass of data coming from this project to the international community, because it could be an excellent sample for doing experimentation and benchmark.
Yes, definitely. It's a very good example for how to preserve 3D digital heritage in a cooperative and a collaborative manner with multiple actors involved. This is definitely a very good example. Yeah. Okay. Thanks. Thank you again. Tons of thank you from our side, Livio. It was indeed very good presentation. I really enjoyed it. And I hope that the digital version of this on our website will spread more awareness, and people get to know about how the collaborative work is being done for a digital project, digital project preserving cultural heritage. So thank you again for your presentation.
Thank you for the invitation.